Chebyshev's inequality. For any random variable x, with the expected value of x equal to mu and variance equal to sigma squared, then the next inequality is true. The probability that the distance of the values of x respect to the mean, that is the meaning for that is one way to interpret the subtraction with the absolute value, the distance between 2 points. Remember that x is supposed to be a random variable, so it has infinitely many values. Well, that depends on the variable, but it has in general many values. So we can interpret this as the distance between all the values of x with respect to the mean mu is greater or equal than k, is bounded by the variance divided by the number k raised to square. Or equivalently, the probability that x minus mu is less than k is 1 minus sigma squared divided by k squared. The two statements for the two inequalities for this probability, they are true. Both are correct. But we say that this one is the upper bound form. And this one, lower bound form. And here I should put greater or equal. So this Chebyshev's inequality gives you a bound for, well, either an upper bound or a lower bound for the corresponding probability of this. The distance between x and m is greater or equal than k, where k is positive. And the distance between x and m, if it's less than k, is at least 1 minus sigma squared divided by k squared. Lower bound and upper bound, probability of x minus mu greater or equal than k is no more than sigma squared divided by k squared. Upper bound, lower bound. All right, let's take some example for this. First one. An instructor believes the distribution of scores on her final exam will have mean equal to 61. Mean of 61 and a standard deviation of 9. I know that in the Chebyshev's inequality, it mentioned the variance, and we are given the standard deviation. But remember that the standard deviation is only the variance. Yeah, I mean it's the square root of the variance. I mean, so well, I will write it down later. But don't forget this. I mean, if you have the standard deviation, you can have the variance, and if you have the variance, you can have the standard deviation. And then Fred's a student in the course that was selected at random. Provide answers to the following to 2 decimal places. First, here we have to define a random variable. X be the random variable representing the scores on the final exam. With mean represented by mu equal to 61. And variance or standard deviation, this is standard deviation, only sigma, equal to 9. Again, in the theorem, we have variance, that is sigma squared, represented by sigma squared. But if you consider only sigma, you have the standard deviation. So we have this information is going to be important. Now, first it says a fine upper bound on the probability that Fred will not score between 46 and 76. Will not score. So in this case, we have to use the Chebyshev's theorem in the next way. First, we have to find an upper bound. So the form of the Chebyshev's inequality we're using is this one, upper bound. So we know that the probability that x minus mu is greater or equal than k is no more than sigma squared divided by k squared. We need to find the number here, but to find the number we need to find k. So this is the same as probability that the scores x minus the mean is 61, is greater or equal than k. It's no more than sigma squared, that is what? Sigma is 9 squared divided by k squared. So here, so we can get the upper bound, we need to find the value for k. But notice, in this kind of exercises, you have to set this difference in the absolute value, set x minus 61, I'm sorry. What are the values we're given? Find upper bound the probability that Fred will not score between 46 and 76. These are particular values for x, for the random variable x, for scores, 46 and 76. What you will have to do in order to get the value for k is to choose any of these two limits, I mean 46 and 70, or 76, and replace the x here by those values. For example, here for 46, we set 46 minus 61 is equal to k. Yeah? And so for k, 46 minus 61 is only the absolute value of negative 15. That is equal to k. But this is only 15, so k is equal to 15. Once you have the value for k, now we can compute the upper bound. So that the probability that x minus 61 absolute value is greater or equal than 15 is no more than 9 squared divided by 15 squared. and this is probability x minus 61 is greater or equal than k, that is 15, is no more than 19, oh, I forgot the square here. 9 squared divided by 15 squared, that is approximately 0.36. And you can verify to see the answer, right? Yeah, I know. I know we can do this because we're using the Chebyshev's inequality. So that this is what we have to do. But notice, I know it says Fred will not score between 46 and 76. Well, it turns out when you say the absolute value of x minus 61 is greater or equal than 15 or greater than 15, here this implies two things. That x minus 61 is greater or equal than 15, or x minus 61 is no more than 15. One of the two. So when you simplify this, you will have a 61 plus 15 is 76. So the first case becomes x greater or equal than 76, or x no more than, I'm sorry, I have to put here negative 15. Negative 15, I'm sorry. Or 61 minus 15. That is 46. So when you have my point is that when you have the absolute value of a difference greater or equal, that means that either the subtraction is going to be greater or equal to that number, or the subtraction is going to be less than the negative number for this number. That's what I set up this two equation. This implies greater or equal than 76 or less than 46. That actually are the values we have here. That's why I can use the Chebyshev's inequality. And to use the Chebyshev's inequality, I have to set up the probability and the inequality and find the value of k. If you have used instead of 46, you have used a 76, you can realize that the answer is going to be 15 in the end, because we have 76 minus 61 is the absolute value of 15, so you will have a 15, right? The value for k. So the answer is this one, 0.36. Next question. Provide a lower bound on the probability that Fred will score between 45 and 67. Again, we will have to use Chebyshev's inequality. So we set up, but in this case, we're using the lower bound. So it's this one. Lower bound is this in this way. So we use probability that x minus 61 is no more than k is at least 1 minus sigma squared divided by k squared. So we have to do something similar here, but in this case we have to find again k, but we notice that we have different numbers. I mean, in this case we have 45 and 77. I'm sorry, let me put this is the part A. and this one is the part B. So repeat it. You have to do the same. You have to set any of these two values, 45 or 77, minus k, and we choose 77. Set 77 minus 61, the absolute value of this, that is equal to k. If you do this, you will have the absolute value of 16 is equal to k, so this implies that k is equal to 16. So this implies that the probability that x minus 61 is less than 16 is at least 1 minus sigma squared, that is 9 squared, divided by k squared, that is 16. And if you do it, this part is equal to 0.68 354 375. That is the answer we have here. And the same, one note, the same as before. When you have the absolute value but different, less than k, this means what? Note, x minus 61 no more than k imply that the distance between the values of x and the mean 61 is no more than k. This is equivalent to say that x minus 61 is no more than k or greater than negative k. That is the meaning. So that's why I could use the Chebyshev's inequality, because in the part B, because it's asking for between 45 and 77. If you replace the value for k that we got, that is 16, notice, if you manipulate this inequality, you will get x less than k plus 61, negative k plus 61. What did I do here? I only added at both sides 61 to cancel the 60. I mean, at both sides, it's like we have here like three sides, right? Because we have this part, and this part. But the point is that I cancel the negative 61. How? By adding 61. 61 here, 61 here, negative 61 plus 61, they cancel out, and 61. And if you use the value for k that we get, you will realize that this is equal to 76, and 16 minus 61 is equal to the value we have here, 45. Yeah. All right. This is only a note, so you can understand. Maybe if you're not used to work with the difference of absolute values, but that is one interpretation. And the point is that the probability that x minus 61 is no more than 16 is at least 0.6835427. All right. Now, central limit theorem. Let x1, x2, and so on be a sequence of independent and identically distributed random variables. With mean expected value of each xi equal to mu, and the variance for all of them equal to sigma squared for any n. Then, if we define this random variable that I'm going to call here random variable sample mean. Then the probability that this random variable minus mu divided by sigma over square root of n is less or equal than a is approximately the probability that c is no more than a when n goes to infinity. All right, I know that this in this way maybe it's a little confusing and it doesn't say so much, but of course I will explain some things, all right, for this theorem that is very, very important. First, note the sample mean or the sampling mean, this one here, this is not a number. Maybe you have seen this symbol before when you compute the mean for a given data set of one variable. But here, this is a random variable. Representing all the possible means for samples with size n. First note. Next, the expected value of the means turns out that it's the same as the mean for all the random variables. I mean, when I say sequence of independent and identically distributed random variables, I mean that all the random variables x1, x2, x3, and so on, they have the same mean and the same variance. The distribution is the same. For example, we can say that for all of them is normal, or for them is uniform. They have binomial, they have exponential, whatever. But the point is the same distribution with the same mean and the same variance. Or then, if we have the variance, remember we can have the standard deviation. So we have this, the mean of the sampling or the sample mean is the same mean as the mean of the original random variables, and the variance is equal to the variance of the is equal to the original variance divided by n. This means that the standard deviation of x bar is equal to sigma over the square root of n. Now, this theorem says that the behavior as to probability of this random variable is normal. Oh, I didn't specify that. I'm sorry. But this is a distribution we have seen before. C is the standard normal distribution. This is normal distributed normally distributed random variable with mean 0 and standard deviation equal to 1. C is a standard normal. It has the standard normal distribution. The standard normal distribution is a random variable with a normal distribution, but the mean is 0 and the standard deviation is 1. So what are we saying here? That the behavior of x bar minus mu divided by sigma over square root of n is, as n goes to infinity, it is the same or can be approximated by the a standard normal distribution. Essentially, we're saying that we can approximate the probabilities for this random variable by using a standard normal distribution. That is what the central limit theorem says. You can approximate, like, general way to say it is that you can approximate the probability that for the means or for the sampling mean by using a standard normal distribution. Essentially, is that. But well, here as a rule of thumb, as a general rule or rule of thumb, the approximation is good for when you have the size of the sample greater or equal than 30. By the way, this is called standard deviation or standard error. All right. Now, let's see one example to understand this. I'm going to explain one example. We have other example that is going to be on web work. Anyway, you have any question about that, you can let me know. Example. It says 45 numbers are rounded off to the nearest integer and then sum. if the individual round-off error are uniformly distributed over -0.5 and zero point 0.5, what is the probability that the resultant sum differs from the sum by more than 5? All right. First, here, notice when you do this kind of problems, you will have to find like the size of the sample. In this case, we can interpret that the 45 numbers is like we are taking a random variable for each of them, but they have the same distribution. That is, in this case, uniform distributed over -0.5 and 0.5. Remember, we have seen before the uniform distribution. 45 numbers are rounded off. So here, x1, x2, and so on up to x45 are random variables representing the errors. I mean, what's going to be the error respect to each of the number that are rounded off? What is going to be the errors? They are distributed uniform between -0.5 and 0.5, but this random variable, they represent that. We want to know what is the probability that the sum for this they differ from the exact sum by more than 5. So in this case, first, xi has uniform distribution. For I equal to 1, 2, 3, and so on, up to 45. The mean for all of these random variables, the mean is the same, and it's going to be the mean of the uniform distribution. If you remember, I said before in a previous video that the mean of a uniform distribution is you have to add the values of the endpoints of the interval. This plus this is -0.5 plus 5 divided by 2. But it's only 0. So in this case, the mean is 0. And the variance is equal to the formula for the variance is the right endpoint minus the left endpoint, 0.5 minus -0.5 raised to the square divided by 12. And if you do this, you will realize that the variance is equal to 0.5 negative 0.5 or minus -0.5, negative and negative positive. So we have 1 squared, so it's only 1 over 12. 1 over 12. So in this case, we can say that mu is equal to 0 and sigma is the square root of 1 over 12. There you go. Why this? Because remember, you have the variance, you can have the standard deviation by computing the square root of the variance. All right, we have this. Now, what are we looking for? what is the probability that the sum of these random variables? So next, we look for the probability that x1 plus x2 and so on up to x45 is the probability that the resultant sum differs from the exact sum by more than 5. So it has to be more than 5. But we can do this in two ways. I mean, maybe we can have a negative difference. So we're looking for this plus the probability that the sum is less than -5. So we're looking for this and this. But since we have symmetry here, it's going to be enough if we compute it for one case, and the other one, the value is going to be the same. So first, let's focus on first on this one. Probability of x1 plus, probability of x1 plus x2 and so on up to 45 greater than 5. Notice, how can we use the central limit theorem to compute that? We can do it because here we have a sum of random variables that they are identically distributed, they have the same mean, and they have the same variance or standard deviation. So when you have a sum like that, you have to turn this sum into something you can use that is related to the central limit theorem. The central limit theorem says, notice, talks about the distribution of the sample mean. So the sample mean is defined by the sum of the random variable divided by n. So in this case, if we want to have this, we need to divide the sum by n. In this case, n is equal to 45. So divide by 45 this side, and divide by 45 the other side. 5/45. And there you have. So this results, the probability, all of this becomes C. Becomes X bar. This is X bar. So this means the probability that X bar is greater than 5/45. But this is what? This is the sample mean. Now, this sample mean, according to the central limit theorem, this probability is approximately the probability that, no, I'm sorry, I forgot something. I'm sorry. The probability that X bar, notice, when you once you have the set up the probability in terms of the sample mean, now go to the form of the central limit theorem, subtract mu, in this case mu it's 0, check it, 0, so x minus 0, and divide all of this by sigma over square root of n. Sigma over square root of n. So it will be sigma, but the value for sigma here is the square root of 1 over 12 over the square root of n, that is square root of 45, is greater than 5 over 45 minus 0 and divided by the square root of 1 over 12 divided by the square root of 45. And now this, all of this becomes C, or it can be, can be approximated by C. C. So now we have this is approximately, this symbol means approximately is the probability that C is greater than the number. And if you compute the number, you will realize that this is equal to 2.58198897. And you can look for this by using the application that I recommended. The application that I recommended here was this one. Look for normal, set mu equal to 0, sigma equal to 1, here probability x greater than, and put the value for x here. In this case, the value is 2. Oh my god, this is updating right now? I'm sorry. So type this value 2.5819, 2.5819, 88897, and you will get 0.004912. This is 0.004912. So that the probability that the sum differs more than 5 is approximately 0.004912. And because of the symmetry in this case, the probability that the sum is less than negative 0.5, negative 5, is going to be the same, 0.004912. So the answer is only add the two probabilities, 0.004912 plus 0.004912. And if you do it, you will realize that the answer is the one we have here. Point 0.009824. Well, it's rounded up here, right? But that is the answer. All right. For some, however, there are some questions there are theory questions, right? So maybe for some of them, you will need to investigate some concepts in Google. I did this on purpose so you can investigate more about the distribution. Or anyway, you have any question about some of the exercises on web work, please let me know. You can send me an email and I will reply to you as soon as possible. See you later.